Our third example of unbound state is the so-called quantum tunneling. This is also very important. So this time, I don't have a step anymore. Rather, I have a finite region where there's a potential barrier. And this potential barrier can be higher or lower than the energy of the particle. And the potential, besides potential barrier, the potential is U equal to 0 everywhere else. Let's say the length of the width of the barrier is L, and the height is U, or U naught. Okay. So you got a wave coming in, and again, we can separate the solutions into three regions, 1, 2, and 3. Here is the incoming region. The wave comes in, and part of it gets bounced back. So you see coming in, bouncing back. And then in region 3, you have only a wave going forward because it never gets reflected anymore. So that's e to the ikx, right? Now in region 2, that's more interesting. Suppose E is less than U. Just like the plot, E is only this much, U is that much. Then it is exponential function, right? Now normally, the exponential function will only keep e to the negative kappa x, right? But the reason why we only kept that was because that step goes all the way to infinity, so x here goes to infinity. You cannot keep this anymore. But if you only have a finite barrier to tunnel through, x never goes to infinity, so even the positive term, you cannot just throw it away. You must keep it because this positive term does not go to infinity anyway. That adds a new term, e to the positive kappa x. Okay, so look at how many numbers constants we have. A, B, C, D, and F. I didn't use E because I don't want to confuse with energy. And then how do you find all these constants? How do you find transmission, reflection, that sort of thing? Again, there's no quantization of energy. Okay. Well, the idea is the same. The algebra is tedious. What's the idea? The idea is that you have to observe the continuity of both psi and deep psi dx, both here and there. So that will give us 4 equations, even though we have more than 4 unknowns. That's okay. So let's bypass the algebra. Okay, this is a little too tedious. We did a lot of similar work. Let's look at the physics. If you did all these things, what are you going to get? Well, I want to highlight 2 important observations. 2 important observations regarding this setup. One is, what happens if you have a wide barrier? So L is quite large. That means that the chance of this particle tunneling through is not very high, okay? It is not very high. So L is much greater than delta, delta being the penetration depth. Well, in that case, we don't really want to keep this term, do we? Because that term will grow exponentially too large because, kappa times delta equals 1 by definition of delta. But if L is far greater than delta, then kappa times the maximum value L would be far greater than 1. You don't want to keep that because that would mean the wave function goes very, very high compared with here. It makes absolutely no sense. With a wide barrier, the particle has barely any chance to go in. So therefore, we can cross that. So C is almost equal to 0. Okay, C is almost equal to 0. You focus on that. That is the same as if you only had an infinitely wide barrier, because that's when we had this. We didn't have that. Okay, and therefore we can just disregard this and focus only on that. So what is the chance of a particle going in a distance L from here to there? It's roughly psi L squared over psi 0 squared, right? Psi 0 here, psi L there, squared because it's probability density. And then remember, you only keep this term, right? And when x equals L, that is e to the negative kappa L times 2 because you have to square it. So roughly speaking, this is the relative probability a particle arriving here will get there. So relatively speaking, this is the probability amplitude of this outgoing wave compared with the probability amplitude of the wave coming in. Okay, and again, this tells you the tunneling rate, the chance of the particle getting out, emerging from the barrier, is exponentially dependent on the value kappa and the width L of the barrier. We will see that in an example. So that's our first important observation, what happens in a wide barrier. You will have particles tunneling out, but the chance of that grows exponentially smaller as the barrier width L increases. Okay, now our second observation is true only when E is greater than U naught. So when E is greater than U naught, you have actually actually traveling wave everywhere. You don't have exponential. You don't have this. You have traveling wave coming in and traveling wave coming out. But again, part of the wave will be reflected. Okay, so therefore you still have only a certain amount of particles, certain amount of chance the particle can go through because another part gets reflected. But we want to explore the issue of so-called resonance tunneling for this particular case. Here is the issue of resonance tunneling. Again, only true when E is greater than U naught. If you did the algebra, basically just observe the boundary conditions for both x equal to 0 and equal to L, then you do all the calculation for T and R transmission and reflection coefficient, you will get T plus R equal to 1, just as before. Okay, don't worry about how we did that, but it makes sense to you, right? Once you did that, you'll get this. And again, don't worry about the algebra here, but I will write down the transmission coefficient for you. What is that? That is the relative probability of an incoming particle actually tunneling through this barrier and getting all the way to positive infinity. Okay, if that equals 1/2, that means half the particles can actually go through the barrier outwards. And this tunneling probability, look at the denominator. Denominator is 1 plus something, and here's a square, here's a square. So generally speaking, this term is greater than 1. So therefore, T is less than 1 generally, which makes sense. Only part of the particles get tunneled through, another particle gets reflected. Okay. However, you see here, there is a sign function here, which I can take to 0. Which I can take to 0. And if that equals 0, what happens? You kill the entire term here, T becomes 1. This is when 100% of the particles go through. Okay? This is called resonance tunneling. Resonance tunneling. Now, when does that happen? Well, we know what K is, we know what kappa is. In this case, I have to write E ahead of U naught, not U naught ahead of E, because again, E is greater than U naught, all right? That's the case when you have resonance tunneling. So resonance happens when the sine square equals 0. That's from math, when T equals 100%. So what's the physics? Well, you know, when KL equals n pi, that's when you get a sine squared KL equal to 0, right? But actually, kappa L. But kappa equals this. So you can actually solve for E and E equals that, okay? Because you plug in the value of kappa squared from here, you get this. So you see, the energy of the particle for resonance tunneling cannot just be any value. It must be U naught plus something n squared. N equals 1, 2, 3, 4, and so on. And does that mean we have a quantization condition? Does that mean the particle can only have this much energy? And the answer is absolutely no. Okay? The energy of the particle can be anything. Again, can be anything. I have this particle coming in. Again, the particle does not see this barrier until it gets close by. There is no reason why the particle at infinity should care about this barrier, so it can have any energy you want. You give it a push, the particle comes in at whatever energy you give to it. But if the energy of the particle happens to satisfy this, is one of those values, then something miracle happens. The particle will make its way through the barrier as if the barrier does not exist. Keeps on going. Eventually, 100% the particle goes through. No chance for the particle to get reflected. So this is the condition for resonance tunneling. It doesn't mean you have to have this energy. Okay, all it means that if you did have this energy, the tunneling will be 100% efficient. That's what it means. So what's the reason behind it? Well, you know that kappa or K, whatever it is, actually equals 2 pi over lambda. It actually represents the wave vector in this region, in this barrier region. So KL equals n pi is the same as L equals n lambda over 2, because K equals 2 pi over lambda. Okay? Now, we can plot L equals n times 2 over lambda like this. This is n equal to 1, n equal to 2, n equal to 3. And this looks very familiar, doesn't it? What is this? Well, this looks like standing wave on a string, right? Okay, remember in physics 1b we did that experiment, and we found that if we satisfy one of those resonance conditions, what happens to the amplitude? Very large. Okay, very large. And that is because if this is satisfied, lambda over 2 in fact is the width of each loop. So you have n number of loops. So you have fit infinite integer number of loops in the integer equals 1, 2, 3, and so on. The reflected wave and the incoming wave, they enhance each other. You have resonance. That's what resonance means. Okay, the reflected incoming wave do not cancel. They enhance each other, and as a result, you have large amplitudes. Right? That's what we saw in that experiment. Right? Large amplitude. So the wave is quite high in amplitude inside. Therefore, it can make it out also with high amplitude. That is why we have the so-called resonance tunneling, and that's the physics right here. Okay, remember I said we had two important observations for the tunneling problem. One was the exponential dependency of the tunneling rate on the width of the barrier, and the other is the resonance tunneling thing. Okay, so we'll look at applications of them. Here's our first application in real life for tunneling, the so-called theory of alpha decay. Theory of alpha decay. It was first proposed by George Gamow. What is alpha decay? Well, alpha decay refers to a certain type of spontaneous nuclear fission where a large nucleus splits into two by spitting out an alpha particle. An alpha particle really is the nucleus of a helium atom. It's got 2 protons and 2 neutrons, so it's positively charged. Okay, and when it splits into 2 pieces, we say an alpha decay has taken place. You got a new nucleus plus an alpha particle. And the funny thing about alpha decay is that for every nuclear decay, we can define what's called a half-life, and that is, on average, how long do you have to wait till the nucleus decays, or half of the nucleus decay? This is called half-life. And it turns out the half-life for alpha decay depends. Why it varies a lot from nucleus to nucleus, and it varies by many orders of magnitude. It's incredible. In fact, you see this table here. Uranium-238, that's a very common radioactive element, uranium-238. It takes an average of 6.5 billion years, okay, for half of the uranium-238 to decay by alpha decay. But this radon-226, it takes still quite long, but a lot less than that. It's 2,300 years. And its isotope, 224, takes only 5.3 days for alpha decay to take place. And those two are just incredible. This guy takes 79 seconds for the alpha particle to decay on average. This guy takes 0.44 microsecond. So why is such a huge difference between the half-lives of these alpha decays of different radioactive isotopes, radioactive elements? George Gamow had an excellent theory on that. You will see a little bit more in nuclear physics. This is what happens. Okay? What I plot here is the interacting potential energy between the alpha particle and its parent atomic nucleus. Now the nucleus is positively charged, as you know, so is the alpha particle. So once the alpha particle is outside the nucleus, they repel each other by Coulomb repulsion. Okay? The Coulomb repulsion is Q1, Q2 over R, and Q1 is the charge on the alpha particle, and Q2 is the charge on the remaining atomic nucleus. And this, of course, goes like 1 over R. Right? You get closer, that's higher the potential. And the size of the atomic nucleus, R naught, is of the order of Fermi, 10 to the negative 15 meters. For the uranium-238, it is about 7.4 Fermi. Okay, so an alpha particle and a nucleus, as they get as close as 7.4 Fermi, they will still be repelling each other, and the repulsive potential energy, you do this calculation, you plug in 7.4 times negative 15 meters, you get 35 MeV. Okay, you get 35 MeV. On the other hand, if the alpha particle is trapped within this range, then something new takes over. There is a dramatic drop in potential because another type of force, much stronger than the Coulomb force, takes over, and that is the nuclear force, the strong nuclear force. It's always attractive, and that's what's holding the positive particles in an atomic nucleus together, despite their Coulomb repulsion. Okay, but this force is short-ranged, so outside R naught, it doesn't exist. and therefore only Coulomb force persists. Okay, so you have basically just a potential hump like this. Right? Now, a particle, an alpha particle, originally is inside the atomic nucleus. It's somewhere here. It's somewhere here. And it's got a certain amount of energy. Okay? It's got a certain amount of energy. And this energy, generally speaking, is less than 35 MeV. In fact, if you look at the case of uranium-238, you find that after it decays, you can capture that alpha particle on its way out. So the alpha particle is now going this way. Right? And when you capture, you find its energy is only 4.3 MeV. So this particle only had 4.3 MeV inside. But somehow it managed to surmount this much taller barrier of 35 MeV on its way out. Okay? That's not easy, is it? You have to face a wide barrier and a very tall one too. And the chance of that happening is e to the negative 2 kappa times L. L is roughly from here to there, something like this. As exponential dependency on kappa and L. And this kappa is 2m u minus e over h bar squared, and then you take the square root. Okay? So you see, if u is far greater than e, then you have a large kappa and you have a large L here as well. This is when the energy of this alpha particle is pretty small to begin with. When it's trapped inside the nucleus, it's E1. Like in the case of alpha particle, 4.3 MeV. It has to overcome a 35 MeV barrier. U minus E is quite large. And also, look at this hump. The hump is wider at the base. It's not like this, right? It's wider at the base. So when you have a small energy to begin with, you have to overcome a tall barrier and overcome a very wide range. This is difficult to do. And this is a very sensitive function. Remember, I added the factor 10 to this. I added length factor of 10 to this. So you go from delta to 10 delta. The probability went from like 13% to 2 in a billion percent, right? Remember that? Okay, so it's a very sensitive function of both the length, the width, and the height of the potential barrier you have to tunnel through. On the other hand, if you had a particle with energy that's already pretty high, so you have an alpha particle with enough kinetic energy inside, then you see it's got a double advantage. First of all, it doesn't have a very tall barrier to overcome, so U minus E is pretty small, so K is relatively small. And the second thing is it has a much shorter width to tunnel through instead of a large wide. So both kappa and L decrease. So imagine if kappa decreased by a factor of 5, say, and L decreased by a factor of 5, then you're looking at e to the negative 5 times 25 times 2, that's e to the negative 50. That is an incredible ratio, e to the negative 50. It's almost equal to 0. So if this guy, compared with that one, if this guy has only 1/5 of the height to overcome and 1/5 of the width to overcome, the chance of this guy going out than that one, the relative ratio is e to the power positive 50. That's incredible. This explains the huge difference in their half-lives. Look at this. Uranium-238 doesn't have very good luck trying to get out because it sits in a low-level energy, has to tunnel over a wide barrier, over very tall obstacle. So this is how long it is. The energy is this much. Okay, you go from 4.3 to 4.8 to a different nucleus, so the energy is a little bit higher, and that makes the job a little bit easier, and in fact exponentially easier. Okay, that's why the time it takes is much shorter, 2,300 years. And then you don't have to go up a whole lot. In fact, when you go to 8.8 MeV, so you're about a little bit more than double. So you're somewhere here. The barrier is much narrower, and the height is also is shorter. And because of exponential dependency, the chance of tunneling through is much greater, making the half-life incredibly short compared with that. So it is the double exponential dependency of the tunneling rate on kappa and on L that explains the huge discrepancy in the half-lives of these radioactive elements given a modest change in the kinetic energy of the alpha particle. So that is an excellent application of the tunneling theory in quantum physics.